Yeah. There is an crisis in Germany. What are you talking about? I know it's already. The winter has come. Yeah. You know what, Germany? Germany got shafted because they're like, oh, let's build a boat too. And they're like, how long do you stay? I don't know why. There's a movie.
Okay. All right, can you guys hear me online okay? Okay. All right, good morning. So I had a question online that asked about, shouldn't there be a Unit 3 module? And yes, there should be, but there is not yet. So I've had a delay in getting things posted, which means there's no assessment today ready. And so I'm going to postpone that a little bit. If I post it today, would you guys be able to finish it like by tomorrow night? I'm seeing all these no's. Okay, so Wednesday, Thursday. Okay, so 2 assessments will be due on Wednesday, and then the quiz will be Thursday. And then you'll have another assessment next Monday. Tuesday will be another quiz. Wednesday, we will not have an in-person class, so I'll post another, I'll just post some material, make sure that there's material on there. What? So Wednesday will be an online. This Wednesday will be in person, but next Wednesday, right before Thanksgiving. Yeah. So this Wednesday will be still here in person. Next Wednesday will be an online, at your own pace time to watch the videos. All right, questions about that change in the schedule? Okay. Okay, so this will be the change. And in addition to this, I will get the Unit 3 modules up. And so there'll be more material to be able to watch and support the learning. All right, so last time we talked about we talked about average of a signal. And then we talked about VRMS. We then went through complex power. So understanding that complex power has two portions to it. The real portion, which is the average power, which is equivalent to what we know from like the DC. So it helps to understand the comparison with the DC. And then the imaginary portion, which was that reactive power. We went over the unit differences. So complex power is in volt ampere units, even though it is really watts still. It's just to differentiate that it has a complex power, or that it is complex power. The real portion is in watts because that is similar to what we associate with as the DC. And then the imaginary portion is in volt ampere reactive VAR. Again, it really is watts, but again, it differentiates that that's the imaginary portion of the complex power. All right, then we talked about apparent power, which is just the magnitude of the complex power. Power factor is average power, which is the DC portion, and then over the magnitude and the apparent power. We then talked about power factor angle. So depending on that angle, then you're either in phase, meaning that you're purely resistive, or you have inductive, which looks like it's lagging. And then if it's capacitive, it looks like it's leading. And so those are the definitions we went through, and then we went through the examples and actually finding those values. Any questions about that so far? Okay. Then we talked about looking for maximum power transfer. And so with this one, we talked about changing this to having the Thevenin. So you have to find the Thevenin in the complex domain. So find the Thevenin, and then from the Thevenin and the derivation that I went through, we want to match the maximum power transfer is when ZL, which is that load impedance, is equal to the complex conjugate of what you find in the Thevenin. So that was where we were. going through an example with this. And then from that, you can then find what that maximum power is by this 1/8 over the VTH, which is VS in that derivation, squared, the magnitude of that squared over RL. This should be RL. All right, so that leads us to where we ended last time. So I'm gonna fix this. This should have been RL. Don't know why I put RR. All right, so we looked at this example and then I was taking the Thevenin of that. So to take the Thevenin, you disconnect the ZL and replace that with, those are your A and B nodes. And then we wanted to find the VTH across that. So doing that, I did node voltage. And so we had this set of equations. And then I was moving from that to write that into a matrix form. So I'm just going to go backwards and start there. All right, I'm going to give you guys a minute. Actually, why don't you guys try to write the matrix form of it, and then you can compare to what I have. So with these sets of equations, try and write the matrix form of that. All right. So you look at the equation and then you're going to lump all of the same variables together. So in this, we have V1 and V2 are unknowns. So I define those as my V1 and V2. So V1 will be my first term, V2 will be my second term. So I highlight each of the V1s. So I have 1 over 2J, 1 over 4 plus 6J. And then in the second column, I'm going to lump all of the V2s together. So I have a minus 1 over 2J, minus J over 4 plus 6J, and then a minus 1 over 4 plus 6J. Yes.
Should it be minus 2JV2?
Yes, thank you. Minus 2, yep. Minus 2J minus 1. Yeah, there is a 2 there. In this, and then I have a minus 8 that then goes over to the other side. And so that becomes my value on the right side of it. So 8, and then the second equation, again, lumping up all of the V1s, I have minus 1 over 2J, and then minus 1 over 4 plus 6J. And then the V2s, I have J plus 1 over 2J, plus 1 over 4 plus 6J plus 2J. So you could write it that way, or you can combine these two together. As this. And then there's no constant value in that equation, so then it's equal to 0. So in MATLAB, I can then set this up to be a matrix of A. And then I set this one up as a matrix of B. And so if you remember from MATLAB, this will be my A. So I use I in this one, so 1 plus 1 over 2I plus 1 over 4 plus 6I. And then I just make sure all my parentheses are correct. Just making sure I put that 2 in the second one. Yep, I did put it in there correctly. And then my B matrix is just 8 and 2. And then all I need to do is define the variable V is equal to inverse A times B. And that will get me my variables V1 and V2. So once I know V1 and V2, how do I find VTH from that? I could go either, well, there's several ways to do it, but I took a loop. So I went a plus V1. And then I did a minus of, I defined this as IX. So minus IX times 4. And then a minus VTH equals 0. And then I defined IX using the node variables V1 and V2. So in that branch, that current is V1 minus 2I minus V2 over 4 plus 6J. So all of the impedance is in that branch. And then I is defined as V2 over minus J or a JV2. So listen. So I defined I as JV2 here, and then I2 is that V1 minus V2 minus 2I over 4 plus 6I, and then VTH as the V1 minus 4 I called it I2 in that one. So using MATLAB, I wrote that script. There we go. So I wrote this as a script. And then when I run it, I can check just to make sure like my A matrix looks right, my B matrix looks right, and then my V is going to be the 4 plus 2J, and then my V2 was -2 minus 4J. And then I and VTH. So here, that's not going to let me do that. I see that VTH is a -2J. Yes.
This IT CTH definition.
I,
Line 11, MATLAB script.
oh, we'll get to that. I haven't gotten to that one yet.
Okay.
So that's the next step. No, that's okay. So this first step is just finding VTH. So ignore the C and the D. That's the next step of this. I just wrote it all as one script. So have you followed me where I've gotten to VTH? Okay. Yes.
So why are you plugging in 2 for B to like the B, and then you have this parentheses 2, and then you have a B right here, a B parentheses 1 minus 2 parentheses 2.
I'm going to change these because my variables, I don't know why I wrote X when I called this I2. I'm just going to erase this one. Okay, so I took a loop here, plus V1 minus I2 times 4 minus VTH. Do you see that loop?
Yes.
Okay. So, and then I2 is V1 minus a 2I minus V2 over 4 plus 6J. You see that?
Sorry.
So this current in this branch, V1 minus 2I minus V2 over the impedances in there, which is 4 plus 6J. Do you see that now? Okay. So that is my I2. So you can see that that's the same in that equation in MATLAB. So on the left, line 5, I2 is equal to V1 minus V2 minus 2I over 4 plus 6. J. And then VTH is just V1, the first equation I have on the right, V1 minus 4I2. Does that answer your question?
You're putting 1 into that matrix. You don't have a matrix B, right?
Yeah, so V is this. This is my matrix V, which is just V1 and V2. So this is A times V equals B.
So then with my I2, when we you're just following with those, what's that B matrix? Location 1, 2.
Yep.
Okay.
So my V equation there is V of 1 is V1, and then V of 2 is V2.
Okay.
Yeah, do you follow that now?
Yeah, I was just confused by
No worries. All right, other questions? Do you guys follow that? Okay. So now we know from this, we know VTH, which is that minus So MATLAB result is VTH is minus 2J. So the other thing we need to find is now RTH. Yes. Yeah, it did. Thanks. Interesting. Screen sharing ended abruptly. Yeah, sorry about that. Okay. Do not see the screen. Okay, hopefully we're good online again. All right, so from this MATLAB result, we get VTH is minus 2J. Now we need to find the RTH. So for RTH, and when you have a dependent source, you remove the independent sources. So then you're going to add either an external current source or voltage source. I see if I add a voltage source here, I know automatically what value will be at that node. Removing this becomes a wire, so I tend to just put a 1. If I put on a voltage source, I'm going to find the current source. If I put on a current source, I'm going to find the voltage source, and then RTH, or I should say ZTH in this case, because it's complex. ZTH will be V over I. And so I can again set this up to be a node voltage here. Make sure I use the same variables. Okay. So go ahead and take a minute to write those equations, and then we'll compare. So here you're going to have 3 equations. So you seem a little confused about this one. So
No, it makes sense now. I figured it out.
I can quickly, so VTH and RTH.
Yeah.
So if I remove this and short this and add on an external test source and find I-test, you can see that V-test over I-test will equal R-test.
Would that be the same thing if we had a current source, would you instead of having an open circuit there instead of a short circuit?
What do you mean by,
Yeah.
oh, yeah.
Yeah.
Well, whatever,
Yeah.
Yes.
you want to look at it that way, yeah.
Yeah.
Would be whatever source you put on here, current or voltage, this becomes then an open. Whoop, and I removed everything else. And then, you know, V test over I test. Yep. And if you put it on current source, it would just be the current times that resistance.
Yeah.
And so that would give you the V test. So that is why. And if you don't know which direction the current, if you think about it this way, like the current has to go into the circuit.
Yeah.
Does that answer? Does that clarify? You seem very confused about that for a minute. Okay. Yeah. Oh. Just because it's easy to add and subtract. I could leave it in the variable form V test, but one is just way easier for me to add or subtract.
Okay.
So whatever variable you, or whatever value you put it at, you would just put that value in the Z test, ZTH equation. So 1 over the top over I test. But you can leave it still in variable form if you want. You can just call it V test. But then it's, I don't know, I like 1.
All right, yeah.
It's almost like. Yeah. Yeah, it's in the basic. Yeah. Yeah. Oh, yeah. Well, yeah.
So go ahead and compare your equation sets to these equations and see if you're able to get the same ones, or if you have an error, or if I have an error, let me know. All right, so these equation sets correspond to the same number. So one is at V1 node, equation 2 is at V2 node, and equation 3 is at the V3, or equation 3 is at the 3 circle node. In this, because I'm trying to find I-test will be my variable. So I just make sure I leave that as a variable. And so in this matrix, I'm going to have V1, V2, and I-test are unknowns. All right, questions? Did you guys get these? Yes.
So with that equation out right there,
Uh-huh.
I understand that you got that one minus one B one. That one minus two I, B two, right there.
Oh, wait, wrong one. So that branch right there, you have the node at 3 is 1. And then I have to subtract off. So this is 1 minus 2i minus V2 over 6j. And that would be this term. And then you leave minus I-test as just a variable. All right, other Other questions? Did everybody get these? Okay, seen some yeses. Okay, so now once we have the set of equations, we can write, I mean, you can solve these algebraically if you want, but I don't like to solve them algebraically, and I would make lots of errors. So again, I like to put them into a matrix form, put them into MATLAB, and use MATLAB to actually solve those for me, or for this one, yes, you'll be able to. Yeah. Yes, because I'm encouraging you to use online software for this one. Yes, you can use MATLAB for this upcoming one. So if you like to do this in MATLAB, you can. If you like to write, you know, if you have another online calculator that you like to use or your own calculator, we'll do these too. Whatever you feel most comfortable with, feel free to use those. MATLAB will also solve these if you have the, I think it's the control toolbox, but I like to put them in matrix form. But whatever set of equations, these, you know, you got to just get your set of equations and then you can set them up. So take a minute to just try to write the matrix form now of these three equations with your three variables, V1, V2, and I-test. And then we'll go through and compare what you get with what I have. All right, so here is the matrix. So just make sure that you do have a similar matrix. You can move the variables around. So I wrote it as V1 is the first variable, V2 and I test. And so my column 1 is V1, column 2 is V2, and column 3 is I test. But you can have those variable columns swapped and you can still get the same result. So my column order is V1, V2, and I test. So take a moment to see if you were able to achieve the same matrix. So in the MATLAB code, I called this first matrix C. And then on the right, I called that my matrix D. So that's where you see those matrices. And then I called my variable list V1, V2, I test, or IT. I test, IT. And then I took V1, V2, IT is equal to the inverse of C times D. And then ZTH, because I had I test as my third variable, was 1 over V1, V2, IT 3. And that gave me ZTH was 2.5 plus 0.75J. All right, questions about any of this? You guys following this?
given 7-1 over the I test. I mean,
Uh-huh.
right?
Yep, so it was just, yeah, ZTH is just 1 over I test. I called my variable V1, V2, IT for the,
You're taking the third.
but I'm taking the third one which is where I define my I test in my matrix.
How don't have to switch that equation.
Which equation?
Oh, it's one more. Never mind. That's fine. Yeah.
So that just comes from V test over I test, and I define that V test as 1. Yes,
Could this be achieved using, just one matrix right here? Where we have a feedback that we're finding and then we have the time.
so no, because you're finding V Thevenin, you're finding it because you're removing the load, and then with the RTH, you have to modify that circuit. So they're not the same circuits. So they have to be separate steps, and that's why you've done 2 different matrices.
All right, thanks for explaining that.
Yeah, so try not, yeah, you definitely, they're 2 different separate steps. If you try to combine them, it won't work because they're 2 separate circuits. All right, other questions? Okay. So once we now get ZTH, we can get, we call it the maximum. What we want for ZL is going to be the complex conjugate of ZTH. So we're going to do 2.5 minus 0.75 J. And then we can also find the average power by taking that equation of sorry, I just want to make sure. Yeah. Okay. So then this is our, so 1/8, and take the magnitude of our VTH squared over RL. So looking at this complex impedance, what do these terms mean here? What does the 2.5 mean? So this is my real load, so that would be my RL. And what is this component? It's going to be, what would it be, an inductor or a capacitor? It's a negative, so it's got to be a capacitor. VTH, where did my VTH go? So VTH was a minus 2J. So the magnitude of minus 2J is just going to be a minus 2 squared over 2.5. And this gives me a 0.2 watts. So when you go back to these equations, let's see. So when you plug it, oh. So when you take when you plug this in, you get RL. I do this right. Yeah. So you're going to get RL squared. And then, or 2RL squared. So you get a 4 that comes out and multiplies by the 2. And then you get the XS minus XS, so those cancel out. So then you have just VS squared RL over 1/2 times 4 RL squared. And then the RL squared cancels, so you get 8 on the bottom, 1/8 VS squared over RL. Yeah. So that's where the 8 comes from. All right, other questions? Okay. All right. Okay, we have time to do another problem. All right, and a heads up, on Wednesday, we're going to move to start to do chapter 9. So this is going to complete what we're learning from chapter 8. And so in chapter 9, I'll go over, hopefully I'll have posted some information if you want to look at that before Wednesday. We're going to talk now, start moving to a frequency response and talking about filters. So that will be the topic on Wednesday. 8.51. Okay, let's do 8.51 here. Well, maybe not. Let's see. 8.55. Oh, and I wanted to mention to you guys on the book, if you see that 8.55 has like a star next to it, that means at the back of the book, there's answers for that one. So I've tried to avoid doing those to give you guys extra practice to be able to go into the book and solve them and then check and see the answers to that. So you can go in the back and find this 8.55 answer and have additional problems to work through. Let's see, let's do. I wanted to do it with the, okay, let's do 8.5. Oh no, that one's got another one too. Let's see, 8.6. Trying to find one with the dependent source in there. So 8.55 is the one in the back. It looks like the other ones that have dependent sources or have answers in the back. So I'll let you guys choose 8.6, 8.55, or 8.60 as a current source dependent source, or 8.58 is that one on the top, or 8.55. 8.6, okay. 8.6, let's do 8.6. All right, so for 8.60, even though this one is in the back, again, we have a dependent source. If we don't have a dependent source, how do you find ZTH?
Just figure the A B terminal and then along the terminal A all the way to B.
Yep.
Combine them.
So that's it for the not dependent sources. So that's why I've been going over the dependent sources. These are harder circuits to do. So if you have no dependent source, you're going to remove any independent sources and just take a pathway from A to B. Okay. So that's the easier circuit. With each of those, you know, if you take the pathway, even though they have complex impedances, you treat those impedances just like any other resistor. So if they're in parallel, you treat them as if they're in parallel. If they're in series, you treat it as in series. When you have a dependent source is when you have to take this extra step, redraw the whole circuit and remove the independent source and then leave that dependent source and add an external source. Okay. So that's why we're going through these steps, because this is a harder circuit to do. All right, so the first step we want to do is find, well, you can start with ZTH, but I usually start with VTH. So let's do that one first. So find VTH. So how are we going to do that? What do we do to the circuit to find VTH? So where's our A and our B location that we're finding? Yep, so remove that load and put your terminals A and B where the load was. And this will be where you're going to find the VTH. So when I open that up, what do I notice? And what do I know about this branch here?
So it could be VC. A is VC, right?
So,
Oh, no.
yeah, so there's no current drop here, right? If there's no current drop there, there's no voltage drop across this, correct? So if that was a dependent source instead of a dependent current source, there would be a voltage drop there. And then VTH would not be the same as VC in this. You guys see that?
Can you explain that logic?
Yeah, why?
So the dependent current source, there's current being forced into that branch, but there's no voltage drop. And that is because there's no current being drawn through R3, which is in parallel to it.
Is that just what happens? There's this parallel dependent current source.
So it's happening because it's a floating wire. So even though you have forced current in that branch, it's still a floating wire.
Why is it different if it's like a discrete source? Like, why is it different?
Yeah. So with see how to describe this. So if I say I have 10-volt source, and this is just a battery sitting there, do I have current flow through it? So I can have zero current flow through that. That's the same as if you have a voltage source or a dependent voltage source. So whether it's independent or dependent, it acts the same. Yes, you can have voltage there and you can measure voltage, but because it's sitting there floating on one side or the other, or if I, say I did ground one side, this is still going to be the same if it's floating. If I have a current source that is floating, let's call it 1 amp. It's sitting there. I have current through it, right? 1 amp. What's the voltage across it? 0 volts. If it's just sitting there without any external circuit on it.
Why wouldn't the current source be flowing down?
The first one I drew, you mean? The,
Yes, so that dependent current source, why wouldn't it be flowing out?
you mean this way? So this circuit,
I mean, wouldn't that just go down to the ground?
so if I define that as my ground, when you have a current source given, it is going to be defined by whichever direction it's given in the symbol itself. So that I does go up because it's defined that way.
It's cross our.
How do I describe this? So I think I get what you're asking, and maybe that's where you're confused. So across this, the current, so I take that back. This is not exactly zero. It's 0.001 VC. So it is going to actually be going in its circle. That what your question was about?
Why wouldn't it be flowing out?
So out of here, you're not going to have any current. But actually internally, you will have current flow through there. So I'll take this back. Maybe it isn't zero. Okay, 60.
Oh, right.
So you actually are going to have voltage there. So I was confusing you. Because yeah, you are going to, to conserve energy, you're going to have to go in that circle. So let's set these up. Find V1 and V2. So go ahead and write the equation sets for V1 and V2. Yes. So with the current source, you can have 0 volts across it if it's just sitting there. In this case, and then it would be the same thing if you change that to a dependent source. You can have current and you can still have 0 volts across it.
Yeah. I think the problem above, you said that like it would be 0 or 1 case versus the other case. You said like it was independent and it would be like 0 and then it was dependent. You said it would have some sort of voltage. So I was wondering why you said it would have voltage.
So if it was dependent source, you could have this voltage across it because it's defined as having a voltage across it. So if you were to try and find the voltage here, you're gonna take, whatever voltage is here and then subtract off the 10 volts, but there won't be any current flow through it. In the case that we have here, where we have a resistor in parallel with that current source, that current is gonna force current through that resistor, and that will provide voltage, so it's no longer 0 volts. It's gonna be Ohm's law of whatever I times R is. Yes,
So once again, I know this is not, but like, why is that even exist? Like, why was it not now? Like, 9 times there. Like, if you have that current, there's no resistance.
so there is gonna be voltage here. That's why I raised the V0. That one actually is gonna have some voltage there because of the current source. So VTH is gonna be V2 plus that VX. Say that a little louder. What?
It's an open circuit with all the current that can go towards the voltage. It's happening there. Because it would ignore our three.
So you're not gonna have current in the branches outside of it where I drew 0. But right across the resistor, you're just gonna have, because there's a defined current source, it forces it to go through R3. And so because it's forcing it to go through R3, that's why you have a voltage drop there. All right, so we have run out of time again today, so I will post the solutions for this, so you guys can use this as another exercise. So I encourage you to write, the equations and be able to solve these circuits, and then we're gonna move to filters on Wednesday. All right, any questions?
I appreciate last time I came in to get the exam of second one second.
Yes, I've not gone to that yet. I apologize. It's been kind of crazy.
I just, the reason, because when I go to get that exam, it say looked no anymore. So I had to